All right, as you can see, this is the review for the polynomials test. Covers a good array of different topics. At the beginning, we're going to have the exponent properties. I do have some stuff on radicals, and if you're watching this video before Thursday, then there's a good chance that you haven't seen like all the stuff that's going to be covered in. That one might stand out a little bit odd, but wait till we actually do the notes and it'll make a little bit more sense for that part. All right, let me go ahead and just dive into it so I don't use up too much of the time here on just talking about other stuff. All right, for a problem like this, really what we're trying to test you on here is your use of the product rule, the quotient rule, the power rule, and then also looking at negative exponents. Oh, and one called the zero rule, for these are zero exponent rule. All right, what do I got here? I got two fractions here. Parentheses don't really do too much in this case in that one. And then here, I do have those parentheses which indicate that there's a 2 on the outside. That's going to be our power rule situation here. I have the other fraction, which is all in parentheses, raised to a -1. Now, there's different ways that you can go about doing the problem, but usually what I like to start with is getting rid of any negative exponents that I could in the problem. So to start with, if you have a negative as like an exponent that's raised to the entire fraction, you can use that to just flip over the fraction. Now, in this case, because it's just simply a -1, I can completely eliminate the -1 by just having flipped over that fraction. If you had something like a -2, you can use the negative to flip it over, but you'll still have to deal with the 2 as a distribution. Now, over here, this stuff is kind of independent that I can work on right now if I want to. It doesn't conflict with what I did over there, so I'm going to go ahead and address the 2 that's on the bottom. That would be the power rule. So sort of like what I was describing, if you had something else over here, how you need to use this. So that 2, I'm going to distribute in to each of the exponents that are in here, which is going to, you're going to do multiplication to get the new exponent that goes along with them. So I'm going to have the 5 multiplied by the 2, which is going to give me a 10. And the 2 times 2 is going to give me a 4. Okay, for the top, nothing actually happens with it. Now, it's a little bit of a side note here. If I had a coefficient like the 4 inside of that, you'd want to make sure that you square it as well. But I didn't show that in this example. Okay, now from this point, I've already dealt with the negatives. I've even distributed, so I don't have any parentheses that are left. What we really look at is just the product and the quotient rule from here on out. What I tend to do is I draw one large fraction bar off to the side and do piece by piece with things. So I'm going to look at the 4 and the 2 first. They do reduce down to a 2 because 4 is divisible by 2. So I'm going to keep a 2 on the top. The x's, I'm going to count up my exponents on the top. There's going to be a 3 and a 2, which is going to add up to give you a 5. That 5 compared to the 10 that I have on the bottom, you're really just going to take a difference of them. And since you're bottom heavy with the x's, you're going to keep that difference on the bottom. So between 5 and 10, that difference is 5, 5 greater on the bottom. We'll keep it on the bottom there. For the y's, I have a y to the 7th on top. I do have a y on the bottom. I do have a y on the bottom, which means, where was I? At 5. So if I take that one away, I'm going to get y to the 6th on the top. For the z's, no z's on top. Both of them are on the bottom. So we're going to get a z to the 5th power down there. And that's it. That's the whole problem. All right, number 2. Again, some of the classes you might not have seen this one yet because I have this at the end of like the way that I'm teaching it. But in short, this is the main idea, which you're going to see in the notes. A square root, let's see if I got that up there. A square root can be treated as an exponent, and it represents a 1/2. This will be discussed, of course, in the notes to explain it a little bit more if you're watching it now. Cubic roots will be a 1/3 type exponent. So these types of questions here, what I want to do is write them as a rational exponent. Rational referring to the idea that you have a fraction for that exponent. Okay, on the inside of this, what I have is x to the 1/3 if I treat that as an exponent. The whole thing is being raised to the 7th power, which gets me into power rule. Power rule has you multiply, so the 7 times the 1/3 is going to give you 7/3. If it could reduce, you would reduce the fraction, but otherwise, that's it. You just leave it here and we're good. Now, in the next, a square root, you do have a number that sits here. It's called the index, but if it's a square root, it's an invisible 2. Okay, so as I showed off to the side here, If you have a square root, that represents a 1/2, but you also have a third power. Now, how this is set up versus the other, you would have y cubed raised to the 1/2. But it ultimately still follows under the power rule, which means that we're going to multiply, and you get a y to the 3/2. All right, last, this guy. The bottom, we should be able to put together based off of this example that we just did, but the 5 is the denominator. So we definitely are going to have a z to the 2/5 power that's put together on the bottom. As an option, when it gets to the test, it'll be a little bit more clean cut on how we want the answers, but for this one, you could write it as a z to the negative 2/5. That would be an option that you could use for this. It all just kind of depends on the instructions. Most of the time we want to get rid of the negatives, but in some cases you actually prefer to keep the negative versus having something in a denominator. Okay, question 3. Degrees and leading coefficients. Incredibly easy. The degree is going to be so I already have this worked out, so we don't have to waste any time actually writing it. The degree is just the highest exponent that you're going to have. So I have a 3, I have a 2, and then that would be a degree 0, or x to the 0 power. Which reminds me of one more thing that I want to go back to. Up in question 1, it isn't mentioned in this example, but if you had something like, let's create a new letter w. If you had w to the 0 power, that is the same thing as a 1. So in most of the problems that look like this, if you have anything that's raised to the 0 power, don't accidentally call it a 0 and call everything it multiplies by 0, but think of it as a 1, and you'll realize that most of the time you can just take that out of the problem. And it's more or less just a distractor that's in there, but at the same time testing you on what it means to have a 0 exponent. Okay, anyway, back to number 3. The degree is going to be the highest exponent, so you identify that, and the rest of it doesn't matter. It doesn't matter that 25 is a larger number or whatever the case is. It's because you have a 3 here that makes this the leading term. So you get a degree of 3, and then the coefficient with it, which is your leading coefficient, is going to be a 5. For g of x, it is written backwards just to see if you really know the rules. But this is a constant. This is x to the 4th power, which is actually a fairly high degree. So you're going to have a degree 4, and the coefficient that goes with it is the negative and the 5. Goes along it. So even if you write it backwards, it's not a big deal. Or sometimes if we add in larger numbers, don't get distracted by those as well. It all comes down to where is the bigger exponent. All right, number 4. All right, couple different methods on how you can evaluate a polynomial. I'm going to start with the idea of direct substitution, which is what you've done for the longest time, up until you got to this unit. So direct substitution would want us to take the negative 3 and just to plug it into any spot where you see the x. Okay, so I'm going to have negative 3 raised to the 4th plus a negative 3 raised to the 3rd power and a minus 5. Now for this, really what you want to make sure you keep track of is just your negatives. So if we have you plug in a negative number and raise it to an even power, that's going to become a positive. So this, if you don't know it, turns out to be 81, and then the even exponent is going to make it positive. That guy, 3 to the 3rd power, is 27, but being that it's an odd exponent, that negative sign is going to get maintained. So you keep it, and you have a minus 5. And all together, let's see what we get. We have 81. We're going to be subtracting a 32 from it. So you get 49 as the answer. Okay, now as another option, and to be honest, the way that we really want you to see, really want you to do it on the test to demonstrate you can do the new technique is going to be synthetic substitution. Okay, now you're going to be using synthetic division anyway, so it shouldn't really hurt to use this as a method as well. And we'll get 49 as an answer. All right, for substitution versus division, you do just plug in the number as it is. You don't switch any of the signs on it. Our coefficients are going to be a 1. There's going to be another 1, but you're going to notice that we skip over the quadratic and the linear, so you get a couple of zeros and a negative 5. The general rule here is whatever your degree is, make sure that you have 1 greater than that in your numbers, which makes up for the constant at the end. And yes, the zeros are important. Without them, it Does not work. We'll drop the 1 down. 1 times negative 3 is negative 3, plus that 1 is negative 2. You get a 6, and another 6, negative 18, negative 18. All right, negative 18 times negative 3. 54 becomes positive, and it's positive 54, which group with the negative 5 is the same thing that you got here. Now, kind of debatable on which one you want to use. It depends on what numbers are available in the problems. The first, sometimes it can get way out of hand with large numbers. And then what you see here, the only time we had a larger number was a 3 times 18. Then from there, the adding was pretty straightforward too. But for the test, you must demonstrate that method. You're not going to get a choice. We're going to say that we need you to do it by that one because that is the new concept that we want to see. Now, you're welcome to do direct substitution just to check your answer, but we need to see that method. All right, so for 5, not going to go through all the steps, but generally it's a lot of distribution. I tried to color code it here. So you got the 5x distributing, you've got the negative 2 distributing, and just how it all groups up into that answer. Over here, most important part, when you distribute into the second binomial, that negative gets attached to the 3. So you got to make sure your sign changes here, and we get a negative 21x. And it should just all group together to give you that. All right, getting about halfway there. Okay, 6. Purpose of 6. So I'll say I have it worked out here to save a little bit of time on this. The purpose is that you have a higher degree polynomial. It's only cubed, but it's still high enough that we don't have any techniques that we can use to directly solve this guy. It is possible that you could do factoring by parts. I haven't looked quite at that, but for how the test is concerned, go ahead and assume that. What I'm attempting to do here is to give you a problem that you can't factor with any other general technique. So as multiple choice problem, I'll give you a few different factors that you might be able to relate to the rational root theorem. But here's some factors that are reasonable that could fit this problem. So the approach that I want you to take on this is use synthetic division. I want you to take the opposites of these. So if it's a true root, it'd be the opposite of that number. And we're going to take the opposite, and you can just go straight down the line here. You take the opposite of that, and you do your synthetic division. And as you go through it, you're going to get all these other numbers, but the one you're really looking for is right here. If that turns out to be a 0, then it tells us that this is an actual factor of it, and that's the answer that you're looking for in the problem. If it fails, in the case that you can see here when I add this, that's not going to be a 0, then you can take that out as an answer choice. Say that's not it, move on to the next. All right, so I went ahead and skipped ahead so you wouldn't have to see me go through a lot of them. I've skipped over to that one. The 7 didn't work. Moved down to the 8. You can see I put the positive 8 in. And as I go through all this, and you can check all the work later, it just becomes a 0, which means that this is the answer that we're looking for. So the idea with this is use synthetic division in the test. If you get it on the first try, good for you. Worst case is you got to do it a few times. If you get 3 that don't work, don't just automatically assume the 4th one does and circle that one. Obviously check it because there could have been a little error that you made at some point there. Now, as a follow-up to that question, number 7, referring back to this guy, I want you to completely factor it. So the thing is that you've invested a little bit of work doing the testing, but you figured out that one of the answers is an n minus 8. That means that it divided evenly into it, and I can take this information, which would refer to after dividing, what I have left over my quotient, and set up another equation that's actually just a quadratic. Give me quadratic. By the way, I've switched my letters here from an N to an X. Totally aware of it now. Didn't know I did that earlier when I was setting this up. Okay, now this guy ends up factoring really easy because of the techniques that have quadratics. You're just going to look for 2 things that multiply to give you negative 35, but add to give you negative 2, which would be negative 7 and a 5. Now if I take those 2 answers plus the answer that I have in 6, I can stay at our polynomial in a factored form, which is the answer that I'm looking for here. So not just identifying the others, but putting everything side by side to show this is equivalent to what we had up here, aside from the fact that I used a different letter. All right, then 8. This question, tying together a little bit more with that stuff that we see there. Okay, so it doesn't refer to which problem I want, but I'm still looking at 6 and 7. What I want you to do is graph it and just remember that the x-intercepts are the roots. So I've already got it typed in here, so I can just hit enter. But what I expect to see, here is that the roots that would correspond in 8, a -7, and a -5 are going to, sorry, I don't know if I said negative, 8, a 7, and a -5 are going to be my intercepts. So I'm going to graph it. There's my equation, and there's our -5, there's our 7, and there's our 8. So that they match up. Not going to give you too much information on why I want you to know that specifically for a problem, but there's a connection here. The factors, the roots, the intercepts, that whole relationship, that's together. So maybe if I gave you a graph, you could use that graph to help figure out what the roots are, maybe write a possible equation. There's different things that could occur, so be aware of it, that there's a match within those two. All right, number 9. Higher degree factoring that we can actually do based on techniques. So here's a couple of big ones that I want you to be aware of. Difference of squares within difference of squares. At least that's how I'll describe it. The instructions want you to identify the real solutions, which would be the real roots. Solutions because we have it set equal to 0, but same idea as the zeros or the roots. Okay, now what we're going to do is factor anyway. We have to factor so that we can find out what those are. Now, it's difference of squares. 625 is 25 by 25. You can factor it like this, so we get conjugates. You get conjugates, but they also have squareds in them. But it still works. And you can multiply through them and see that it works. But that'll be our first step with this quartic. Now, the neat thing is that this one right here, that is also a difference of squares. The other one, which has got addition in it, not a difference of squares. That guy doesn't factor any further. It looks like it should. It really does, but there's nothing you can do with it. And that one will end up producing what we call non-real solutions. So for our purpose of the question, that part really just gets discarded, and we take our solutions from here, which will be x is equal to 5 and also -5. 2 answers that work. With a quartic function, you can expect as many as 4, but we just got 2 of them that are real. All right, next, the sum of cubes. This is SOAP. SOAP problem here. Okay, I suggest you write the roots above each of these. The cubic root of 8x cubed is 2x. The cubic root of 64 is 4. And then that way I don't look at the 8 and the 64 anymore, because they're not going to show up anymore. You don't need them. Okay, when it factors, you can get a binomial and a trinomial. The binomial will start with simply dropping those 2 numbers that we just wrote down into these 2 spots. I'll talk about the sign in a moment. The 2x and the 4 are now also going to go here and here. There's 3 terms. They'll be at the front and the end, but when they go in, they get squared. So the 2x squared is going to give you a 4x squared. When the 4 gets squared, you get a 16. In the middle, you get the combination of these 2, which will be an 8x. Now, the only thing that I haven't done yet, so all the numbers are done. The only thing I haven't done yet is put in the signs. And that's where this acronym SOAP comes in. The S is going to stand for same, which means whatever operation I had at the beginning, I'm going to use in this spot. Actually, let me write down the letters here so you know where they go. So that's going to be the same as the start, which is a plus. The next operation is going to be the opposite, O for opposite. So if I had plus, then this would be minus. The AP stands for always positive, which means plus in the back. Now, when it's all said and done, and I want you to know this for the test here, if I'm only asking about the real solutions, this part doesn't matter. it doesn't factor any further, and it doesn't produce any real answers that go with it. The only real answer is here. So if I took the 2x plus 4 and set it equal to 0, we would subtract the 4 first. We would then divide by the 2 and end up with a negative 4 over 2, which is the same thing as negative 2. That's your solution. And you just get 1. That's it. You only get 1 from it. So a good kind of a piece of advice is about these sums and difference of cubes. You're only going to get one real solution. So you can really just take it from that part. That's a consistency with these. All right. Video is getting a lot longer than I expected it would, but we're almost done. Long division, it's mechanical. Make sure that, oh, I do have a typo here, so I decided to let that be a 4x cubed, which you'll see me place in there. But make sure you get any fillers that need to be in there. It's really about asking the question, what do you multiply x squared by to get x to the 4th, which will be x squared. You then multiply that to both of the divisors terms. You get this, put some parentheses, minus, draw the line, subtract, drop down the next number, so on. So I've got this one pretty much all worked out to here, but I haven't stated the answer in the end of it, so I'll let you go through to look at all the steps. But in the end, the answer is taking that quotient that you're going to have, and then after that, we're going to add on our remainder. There's an x in there. We're going to add on the remainder over your divisor. And that's it. Now, by the way, you only add in the zeros if you're skipping over a term. So in this case here, we only got 2 terms for the quadratic, but we're not skipping one. We have the quadratic, we have the linear, the constant is missing. If you're not skipping it, it just cuts off at that spot. You don't need to create a 0 for it. You're welcome to put it in there, but you're literally just going to have a lot of zeros at the end of the lines, and every time you multiply by 0, you get a 0, and every time you add, you just get whatever was there anyway, so it doesn't really make sense to add that one. Though it's a good exercise to see it at least once. All right, and in conclusion, this is the very last topic that I'll be teaching, so if you're watching the video before Thursday, this one's not going to quite make sense yet, but see what you can take from it. In order to solve for x, I'm going to try and isolate it, which is a good idea here because I only have an x written once. The first step is just to move that 20 over. Get that guy out of the way. In fact, that really isn't even the important part to the problem. It's just a little extra work to do. And it helps disguise things a little bit. Because once you see it as 125, I really hope that you recognize 125 is 5 cubed. And that might be important in a moment here. Now, in order to undo an exponent like this, the best method, I think, for just getting moving with this is to use the reciprocal of that and apply it to the other side. And again, in notes, when we cover it, I'll talk more about that stuff. Reciprocal, you get 5/3. Now, from the very beginning, remember that when you have a denominator in your exponent, that actually refers to a root, which means I want to take the cubic root of 125. And guess what the cubic root of 125 is? It's 5. So x plus 7 is actually just equal to 5 to the 5th power, which I'm realizing right now is a really large number. But that's what it is. Okay, so next, I'll go ahead and evaluate this. So we dealt with the 3 on our own. That's cool. It shrunk it down. Now we're going to raise 5 to the 5th power, which without a calculator is a little bit much, but 5 to the 4th is 625. So if we did 625 times 5, we'll get our answer. And I'll just go ahead and cheat here so I know I do it right. 625 times 5 is 3125. So now x plus 7, 3125. We'll subtract that 7. Doesn't change it by much, but it's actually important. You get 18 when you subtract, so done.